Okay, Assalamu alaikum everybody. My name is Baan Alzuhair, and today we're going to be talking about insulin and glucagon. This is going to be a easy lecture, inshallah, and pretty simple, pretty straight to the point, inshallah. And let's get into it. This is the agenda. This is what we're going to do today. As you can see, not many objectives. Inshallah, is easy lecture and really fast. We're going to talk about the cells of the pancreas. We're going to talk about insulin, catecholamines very briefly, glucagon, and we'll take some questions. Let me get the pointer. Okay. Okay. So let's start with cells of the pancreas. Dr. Yaqeen really focused on the histology of it. So I'm going to too. He said that there are three types of cells found in the pancreas that are really important. So first of all, let's start with differentiating between endocrine pancreas and exocrine or exocrine pancreas. Exocrine pancreas is the parenchyma that is found um, around the islets of Langerhans. The islets of Langerhans are the endocrine cells, the endocrine part of the pancreas. There is slide, yeah, this slide. This slide is very good in making you differentiate between the parenchyma or the exocrine pancreas and the endocrine pancreas. These really light areas, lightly stained areas, these are the islets of Langerhans, and we're going to differentiate between each type of cell inside the islets of Langerhans. So this is basically the islets, and we have three types of, well, important cells. The most abundant cell, or the most usually, like most likely filling the islet of Langerhans, is the beta cells. And the beta cell secretes insulin, and it's usually found in the center of the islet. Alpha cells are found in the periphery or at the edges of the islet, and they secrete glucagon. We also have delta cells, which are found in a less amount than the beta and alpha, and they secrete somatostatin. And we also have the F cells, these red ones over here. As you can see, they're not many. They secrete pancreatic polypeptide. So this picture was taken from Dr. Yaqeen's slides. This picture also was emphasized by the doctor. This stain is called the Mallory stain. And in this stain, you can see the beta cells staining orangish. The delta cells are bluish or greenish. You can see blue here, but in other slides, it could be green. But a very different color, or like a standing out color, it's the delta cells. And we have the alpha cells, which are staining red, but I don't think they're very obvious over here. So beta cells, orange, alpha cells are red, and delta are bluish. Over here, this is the H&E stain. This is the normal staining that we see in almost every histology lecture. This is the islet of Langerhans. You can see the line lining it over here. The beta cells would stain a lighter shade of pink, and the alpha cells are usually darker. These are the cells that are found in the islets of Langerhans or the pancreas. These were not really emphasized by the doctor. He really focused on delta, alpha, and beta, and he said these are not important. So I just added the table from his slides to make sure that I don't miss anything. Okay, so let's start with insulin. Insulin is the most important anabolic hormone, okay? It belongs to the gene family that includes insulin-like growth hormones, 1 and 2, IGF-1 and IGF-2, and relaxin. So this information, or like point number 2, was not really mentioned by Dr. Yaqeen, but I thought it was an important piece of information for you guys. You're gonna take it sooner or later. I think you took it in your blog, the gene families for hormones. So the half-life of insulin is around 6 minutes, and it's cleared within 10 to 15 minutes from the circulation. So it doesn't have a really long time to stay in the circulation, so its action is very short. It's degraded or broken down by insulin degrading enzyme. That's kind of obvious. It stands for IDE, or insulinase in the hepatic portal vein. So it starts with its precursor, which is pre-proinsulin, which then gets converted into proinsulin. And then proinsulin is actually insulin bound to a C-peptide. So if you cleave the C-peptide, you'll end up with the active or the mature type of the hormone, which is insulin. So an overview of insulin's role, we're going to go into it, inshallah, in detail later. But I'm just going to give you guys an idea of what insulin actually does. So it increases glycogen storages. That's number one. You increase glycogen storages from using the glucose that you have in your body. So ingested glucose or injected glucose. You use these to turn glucose into glycogen, which is the stored form of glucose. Okay. If you have excess carbs, excess sugar, excess glucose, you turn them into fats and it gets deposited and stored in the adipose tissue. It also promotes amino acid uptake from the food that you eat. And by promoting amino acid uptake, it increases protein synthesis. So this is the basic role of insulin. We're going to go into detail into it, inshallah. So I just mentioned C-peptide and how we cleave it from proinsulin to form the active form of the hormone, which is insulin. So C-peptide is actually used to differentiate between ingested and endogenous insulin. And it's also used to differentiate between type 1 diabetes mellitus and type 2 diabetes mellitus. So in type 1, I think this is general information now, everybody knows about diabetes, but type 1 diabetes mellitus is an issue with the beta cells themselves, okay? The beta cells are not producing enough insulin in your body. But the type 2 diabetes mellitus is also called insulin resistance. That means the cells in your body are making insulin, but the rest of your body are not responding to it. Your pancreas is making insulin just like normal, but your body is not responding to it. It's called insensitivity to insulin or resistance. Your cells are not uptaking the insulin, they're not responding to it. So in type 2 diabetes, C-peptide would be higher than normal because your body is making it. You're fine, and your pancreas is fine. The rest of your body are not responding. And type 1 diabetes, you would see no C-peptide because the problem is with the producer of insulin, which is the beta cells. Okay, so insulin secretion. How does insulin get secreted? How is it stimulated? So the main stimulation for insulin is glucose or blood sugar levels. So glucose binds to a transporter found on the membrane of the beta cells. This transporter is called GLUT2, okay? Once glucose binds to this transporter, it gets taken inside the cell and it gets turned into G6P or glucose 6-phosphate by glucokinase. This is the enzyme that turns glucose into glucose 6-phosphate. And then G6P, for short, is utilized or oxidized in glycolysis, TCA cycle, and oxidative phosphorylation. You guys have taken this in Mol 1. There's no need to repeat it. So the product from these reactions will cause two things: potassium channels to close and calcium channels to open. When the calcium channels open up, calcium rushes in the cell. An increase in intracellular calcium would lead to the exocytosis of granules or vesicles that have insulin or proinsulin inside of them, and insulin gets released into the body. That's basically how insulin responds to glucose, or the body responds to glucose binding to GLUT2, all the way into the exocytosis of the granules. Okay. So insulin secretion, as I said, the main stimulator is blood glucose, but it's also stimulated by other stuff, such as several amino acids. Not all amino acids trigger insulin secretion, but several can do that. Vagal cholinergic innervation via M3 or muscarinic 3 receptors, and also sulfonylurea drugs. These sulfonylurea drugs, they inhibit potassium channels. Remember when I just said that insulin secretion, the product of G6P being used in TCA glycolysis and oxidative phosphorylation would lead to the potassium channel closing. So if you permanently close potassium channels by using sulfonylurea drugs, this would lead to kind of a long-term opening of the calcium channels, and this would lead to a continuous secretion of insulin. So this stimulation happens by increasing CAMP or CAMP and calcium, as I just mentioned, but it's also inhibited by some stuff, such as epinephrine and norepinephrine, and they inhibit insulin secretion by binding to alpha-2 receptors on the beta cells. When are epinephrine and norepinephrine secreted? They're secreted when you're exercising. So when I mentioned the basic role of insulin, I said that they increase glycogen storages by turning glucose into glycogen. So it's stimulated when you have a lot of glucose in your body, or when you have carbs, or when you just have eaten. That's when insulin is secreted. But if you're exercising, you need that glucose and glycogen to be utilized in order for you to have energy. You need the glucose and glycogen as an energy source in your exercise. Epinephrine and norepinephrine inhibit insulin from turning glucose into glycogen. You don't need the stored form of glycogen. Now you're working out. You need the glucose in order to form energy. So epinephrine and norepinephrine protect us from hypoglycemia. They might they protect us from the insulin being overactive, or the increased action of insulin, because insulin is not all good. I know it's the most important anabolic hormone, but it can be evil sometimes. It can turn like normal situations into hypoglycemia. It can take way too much sugar from your body. That's why epinephrine and norepinephrine are here to help. Also, we have somatostatin, which is released by the D cells that we mentioned before from the islets of Langerhans. There are some other hormones that stimulate insulin secretion, but not directly, such as glucagon, glucose-dependent insulinotropic peptide, and acetylcholine. All of these, they increase the intracellular calcium levels. They don't increase insulin itself, like not directly. They increase intracellular calcium levels through other signaling pathways, not like the one we just talked about. And they enhance the effect of glucose. So if there is no glucose in the body, they would have no effect on insulin. Okay, so this is a table from the doctor's slides, and it's a summary of what affects insulin secretion. So what increases insulin secretion, as I said, the major thing that controls insulin secretion is blood glucose. So if you have increased blood glucose, that would increase insulin secretion. You have increased blood-free fatty acids, increased blood amino acids, gastrointestinal hormones like gastrin, cholecystokinin, secretin, glucose, growth hormone, cortisol, sulfonylurea drugs. We mentioned all of these. Parasympathetic stimulation, so not norepinephrine and epinephrine. Beta adrenergic stimulation, and insulin resistance and obesity. All of these increase insulin secretion. What decrease it, we have somatostatin that we just mentioned. Fasting. Imagine that you're fasting. You're not ingesting any food. You're not eating any food. So you don't have any glucose, or you don't have much glucose running through your circulation. Would you need insulin to come out and take whatever is left from the glucose that is found in your circulation and take it into the cells? That would lead to an hypoglycemic shock, especially for the brain. And we're going to talk about it in a bit. So hypoglycemic shock would lead to seizures and even coma and death. So that's why epinephrine, norepinephrine stop insulin from working at certain times. And also we have decreased blood glucose for the same reason. Okay, so GLP-1 was not really mentioned in Dr. Yaqeen's slides, but I think it's a very important piece of information. You can take it as you wish. It's an FYI at the end. So GLP-1 is an incretin hormone. Okay, incretin hormone is found in the GI tract. It's released in the GI tract, specifically L cells that are found in the ileum, part of the intestine. Okay. So GLP-1 is actually the reason why ingested glucose works better than injected glucose. So ingested glucose will stimulate this incretin hormone, or GLP-1, in the ileum, and it will affect insulin faster than injected glucose. and it's secreted upon the arrival of glucose. Once you eat and the glucose goes to the ileum, it stimulates this GLP-1, okay? And it has an effect on beta cells. It stimulates beta cells to secrete more insulin. And it's degraded by DD4, okay? DD4 stands for dipeptidyl peptidase 4. So if you give GLP-1 mimetics and DD4 inhibitors for type 2 diabetics, this is a pretty good treatment solution for type 2 diabetics. GLP-1 mimetics, which increases the absorption of glucose since it increases insulin secretion, and DD4 inhibitors, that just means it prolongs GLP from being activated. It just prolongs its existence. Okay, so insulin gets released in two phases, a rapid phase and a slow phase. The rapid phase is the release of preformed insulin, the insulin that you already have in your cells. And the slow phase is the release of newly formed insulin. And this graph explains exactly that. This spike is the rapid increase in insulin from the release of preformed insulin. And then this slower spike over here, the slower rise in the curve, this is due to the release of newly formed insulin. Okay, so effects of insulin, it has a lot of actions, but all are aimed to decrease blood glucose levels. All of them, they lead to the same goal, okay? So it increases glucose uptake into the cells, just like GLP-1. It increases glycogen formation by decreasing the degradation of glycogen, increasing its formation by decreasing glycogenolysis. I always get confused between these. So it increases glycogen formation, increasing its synthesis. It decreases its degradation, so it decreases glycogenolysis, and it turns glucose into something else, okay, which is glycogen. But it also inhibits glycogen from turning into something that we don't need. So we inhibit gluconeogenesis. We don't want glycogen to turn into glucose. We want the opposite to happen. So we inhibit glycogen from turning into glucose, and we enhance glucose turning into glycogen. I hope everyone understands this. So it also, as I said, decreases glycogenolysis, decreases gluconeogenesis, but it also increases protein synthesis. But this is done by increasing the uptake of amino acids from the blood. It increases fat deposition. This is done by the increase of the uptake of free fatty acids. It decreases lipolysis or lipolysis, and it increases potassium uptake into the cells. All of these are the actions of insulin. These actions have to be memorized and understood very well. This will help you to solve any question you get regarding insulin and glucagon also. Okay, so the last effect of insulin, which is the most important one, is its effect on the brain. So the brain is normally, almost all the time, permeable to glucose without any help of insulin. So the brain only uses glucose as an energy source. This is in normal conditions. The brain's most favorable energy source is glucose. But in desperate times, when someone is starving or in severe dehydration, it may switch to the use of ketone bodies from fats, but with difficulty. And if there is no glucose to supply the brain for a while, it can turn into a hypoglycemic shock, like the one we talked about before. It can lead to irritability, seizures, coma, and even death. Okay, so we're going to talk about the switching between carbs and fat metabolism. When does the body switch from breaking down carbs to get energy to breaking down fats? So if we have low glucose, no insulin would be released, and fat is used for energy, except for the brain. Remember, we just talked about the brain. The brain is permeable to glucose, and it would use glucose until its totally empty until your body has zero glucose left. So in case of low glucose, no insulin would be released and the body will use fat for energy. If you have high glucose, you will have high insulin levels in your body and the carbs will be used for energy instead of fat. There are some other hormones that have a role in the switching between carbs and fat metabolism, such as growth hormone, cortisol, epinephrine, and glucagon. Okay, so effects of catecholamines in blood glucose, they stimulate glycogenolysis. That means they release glucose into the blood by breaking down the stored glucose, which is glycogen. It activates adipose tissue hormone sensitive lipase. This breaks down the fatty acids that is found in the adipose tissue, and it releases these fatty acids into the blood. All effects of catecholamines on this metabolism are via alpha-1, beta-2, and beta-3 receptors on the muscles, adipose tissue, and liver tissue. So catecholamines basically work similarly to glucagon, which we're going to talk about now. So also there's something, just one more point before we go into glucagon. This is an important information that Dr. Yaqeen talked about. He said that insulin and growth hormone work synergistically to promote growth. That's the summary of like almost 2 slides. All you need to know is that growth hormone and insulin promote growth, and they work synergistically. That means they work together to promote growth. And that's basically it. 2 slides, 1 line. So I hope everyone understands insulin. Let's get into glucagon, sorry. So glucagon also has a precursor, just like insulin. The precursor is called pre-proglucagon, almost similar to insulin. It belongs to the secretin gene family. It has a half-life of 6 minutes, also similar to insulin. And it's metabolized in the liver, and insulin is degraded in the hepatic portal vein. So it's only metabolized in the liver and it's not metabolized in the muscle because the skeletal muscle does not express the glucagon receptor. Okay, so let's take an overview of glucagon's role, just like we did with insulin, and we're going to get into more detail of what it does later. So the major role of glucagon is increased blood glucose levels. That's it. That's the major role of glucagon. That's what you have to absolutely pin in your brain, that glucagon increases blood glucose levels. Okay, so how does it do that? I know this picture is not very high quality, but I got it from Dr. Yaqeen's slides and I couldn't find anything better than this picture. So what does glucagon do? It increases blood glucose levels. How does it do that? It increases glycogenolysis. So it breaks down glycogen stores in the muscle and in the liver, and it will turn the glycogen into glucose and make it more available for other organs in the circulation. It increases gluconeogenesis, increases glucose formation, which also leads to increase of glucose in the blood. It increases lipolysis. That means it increases free fatty acids in the blood. And it increases keto acid formation. Keto acid formation comes from the free fatty acids that are found in the blood. So these are the actions of glucagon. Okay, so this cascade of action, Dr. Yaqeen, I'm not sure if he emphasized on it really, but I'm going to mention it. So it activates adenyl cyclase. Glucagon binds to its own receptor and it activates adenyl cyclase, which forms CAMP or CAMP, which then activates protein kinase regulator. That activates protein kinase. And that activates phosphorylase B kinase. And then phosphorylase B kinase gets turned into phosphorylase A, which is kind of the active form of phosphorylase. So phosphorylase A degrades glycogen into G1P, which is glucose 1-phosphate. And then G1P is used in glycolysis and glucose is then released. All of this cascade, I'm not sure if you have to memorize it or not, but I mentioned it because Dr. Yaqeen had a slide on it. So I guess this is I'll just say it one more time. I'll repeat it because it's a really long cascade. So glucagon binds to this receptor, gets inserted into the cell. It activates adenyl cyclase, which activates or forms cyclic AMP or CAMP or CAMP, which then activates protein kinase regulator. Protein kinase regulator activates protein kinase. Protein kinase activates phosphorylase B kinase, which then gets converted into phosphorylase A. Phosphorylase A breaks down glycogen into G1P, or glucose 1-phosphate. And then glucose 1-phosphate is then utilized and released as glucose. Okay, so we have a couple of questions over here. So, can we stop the recording for just 1 second? Okay, so thank you guys for watching. And if you have any questions, please, this is my number. Contact me if you have any. And this is a QR code. Please scan it and give us some feedback. And thank you so much.